There's a quiet puzzle that sits at the heart of how the universe works. A puzzle about energy, about why things run down, why batteries fade, why warmth escapes into cold air, why we can't simply recycle everything. You don't need to solve this puzzle tonight. You don't need to remember anything at all. This is just a space to rest, to let ideas drift past you like slow clouds, to be here without effort, without purpose. Let yourself settle. There's nowhere to arrive. Energy is strange. We use it every day. We charge our phones, we drive cars, we feel the warmth of sunlight. And yet, energy behaves in ways that seem almost contradictory, almost paradoxical. If you've ever wondered why a battery eventually dies, even though we're told energy can't disappear, you're already touching the edge of something profound, something that thermodynamics, the science of energy, heat and change, has spent centuries trying to explain. But tonight, we're not here to learn quickly. We're here to let these ideas unfold slowly, gently, without rush. Think about a battery. It starts full. Over time it drains. The device it powers eventually goes dark. We say the battery is dead. But where did the energy go? It didn't vanish. Energy doesn't vanish. That's one of the deepest truths in physics. Energy is conserved. It can change form, from chemical to electrical to heat, but the total amount remains the same, always. So if the energy is still there, why can't we use it anymore? This is the question we'll circle around tonight. Not to answer it quickly, but to sit with it, to let it breathe, to understand slowly that there's a difference between energy existing and energy being useful, a difference between having energy and being able to do something with it. The first law of thermodynamics tells us that energy in an isolated system is conserved. It can change from one form to another, but it's neither created nor destroyed. This is an absolute rule, a bookkeeping rule in a way. Energy in equals energy out. When you burn fuel in a car engine, the chemical energy stored in gasoline becomes motion, heat, sound, and exhaust. Every joule is accounted for. Nothing is lost. When a hot cup of coffee cools down, its thermal energy spreads into the surrounding air. The energy doesn't disappear, it redistributes, it moves, but it remains. This conservation is fundamental, reliable, unyielding, and yet, despite this conservation, something changes, something degrades. Many processes in nature evolve spontaneously towards states where less work can be extracted from the same total energy content. The energy is there, but its ability to do work diminishes. You can feel this in your own life. A warm room gradually cools. A spinning top slows and stops. A stretched rubber band loses its tension over time. The energy hasn't vanished. It's still present, still real, still measurable, but it's become less useful. This distinction between conserved energy and decreasing usable energy is central to understanding entropy, central to understanding irreversibility, central to understanding why we can't simply reuse all the energy around us, even though none of it ever disappears. You don't need to grasp this immediately. You don't need to hold on to it. Just let the words settle. Let the idea rest somewhere in the background. There's no rush, no test, no goal, just the slow unfolding of a truth about the universe. A truth that's both simple and profound. A truth that explains why engines wear out, why ice melts, why we can't turn back time. The first law is beautiful in its simplicity. energy is conserved, but it doesn't tell the whole story. It doesn't explain direction. It doesn't explain why some transformations happen naturally while others never do. Why heat flows from hot to cold, but not the reverse. Why gases expand to fill a room, but never spontaneously compress themselves back into a corner. Why a broken egg never reassembles itself. In classical thermodynamics, the first law expresses conservation of energy for macroscopic systems. It ensures that all energy transformations can be accounted for in terms of internal energy, heat, and work. Heat, in this context, isn't a substance. It's not a fluid that flows from place to place. That was an older idea from centuries ago. We now understand heat as energy transfer due to temperature difference, a process, a flow, a redistribution. When you touch something hot, energy moves from that object into your hand, not because there's a heat substance moving, but because the microscopic particles in the hotter object are moving faster, and through collisions and interactions, some of that kinetic energy spreads to the particles in your cooler hand. Modern treatments view thermal energy as part of the internal energy of a system, energy associated with the microscopic motions and interactions of countless tiny particles. Not a separate entity, just one form of energy among many, and still, energy is conserved. Every real process merely redistributes energy among different forms. It does not eliminate energy, cannot eliminate energy. This is absolute. This is reliable. This is known. But here's where the puzzle deepens. Here's where conservation alone isn't enough. Because while energy is conserved, its usefulness, its ability to perform work, to drive change, to power devices, is not conserved. That capacity diminishes, degrades, slips away. You don't need to understand why yet. You don't need to hold on to every detail. Just notice the distinction. Notice that something else is at play. Something beyond conservation. Let yourself rest here for a moment. Let the words wash over you. There's no need to remember. No need to track every idea. Just breathe. Just be. Thermodynamics speaks of something called free energy. Not free in the sense of cost, but free in the sense of availability. Free energy is the portion of a system's total energy that can be converted into mechanical work under given conditions. It's the useful part, the part that can still do things, drive engines, charge batteries, move objects, sustain life. As systems evolve toward equilibrium with their surroundings, the fraction of energy available for work shrinks. The total energy remains constant, always constant, but the free energy decreases. This is what happens when your coffee cools. The thermal energy spreads into the room. The total energy of the coffee plus the air is unchanged, but the ability to extract work from that temperature difference, that ability fades, diminishes, becomes negligible. Free energy, in thermodynamic terms, quantifies the maximum work that can be extracted from a system interacting with a thermal reservoir under specified constraints. When processes occur spontaneously at constant temperature and pressure, free energy tends to decrease, even though total energy remains constant, even though conservation holds. This reflects the system's loss of capacity to do work, a loss that's irreversible, a loss that's built into the fabric of how processes unfold. Once energy has been spread out as low-temperature heat close to the temperature of the environment around it, only a small fraction can be further converted into useful work. The energy is there, still there, conserved, real, but it's no longer accessible in the same way. It's become diffuse, scattered, equalized. You can feel this in everyday life. When you brake a car, the kinetic energy of motion doesn't disappear. It converts into heat in the brake pads, the wheels, the air. That heat energy is real. It warms the materials. But try to capture it. Try to use it to push the car forward again. You can't. Not without expending more energy from somewhere else. The energy from braking has degraded into a form that's no longer useful for propelling the vehicle. This is the heart of the matter. This is the puzzle. Conservation tells us energy persists, but experience tells us usefulness fades. And this fading, this degradation, is governed by something called entropy. Let the ideas drift. Let them settle without effort. There's no need to grasp everything at once. No need to hold on. Just rest. Just listen. The second law of thermodynamics introduces something new, something that conservation alone can't explain. It introduces direction, an arrow of time. Certain transformations happen spontaneously in one direction, but not the reverse. Heat flows from hot to cold, never the reverse without external intervention. Gases expand to fill available space, never spontaneously compress. Mixed fluids don't unmix themselves. These aren't just preferences. Their regularity is so consistent, so universal, that we call them laws. The second law states that for an isolated system, entropy does not decrease in spontaneous processes. Entropy may stay constant in idealized, perfectly controlled transformations, what we call reversible processes, but in real, natural processes, entropy increases, always increases, never decreases on its own. Entropy is a state function, a property of a system that depends on its current condition, not on how it got there. And for isolated systems, systems that don't exchange energy or matter with their surroundings, entropy tends to increase over time, or at minimum to remain constant. It does not spontaneously decrease, not in macroscopic systems, not in the everyday world we inhabit. This is an empirical law, a law built on centuries of observation and experiment. It's not derived from more fundamental principles in classical thermodynamics. It's simply observed to be true, universally true, deeply true. And it's supported by statistical mechanics, which connects the macroscopic behavior of systems to the microscopic behavior of countless particles. But you don't need to follow every thread. You don't need to trace every connection. Just notice. There's a directionality to nature, a preference, a tendency. The second law forbids certain things. It forbids the complete conversion of heat from a single thermal reservoir into work in cyclic processes. This is why heat engines, car engines, power plants, steam turbines can never be perfectly efficient. Some energy must always be rejected as waste heat. Always, without exception. This isn't an engineering limitation. It's not about better design or superior materials. It's a fundamental limit imposed by the second law. The second law underlies the observed irreversibility of everyday phenomena. Frictional heating, diffusion, heat conduction from hot bodies to cold ones, mixing, dissolving, combustion. All of these processes move in one direction. They don't reverse themselves. They can't reverse themselves, not without external work, not without increasing entropy somewhere else. Let yourself rest with this. Let the idea sit gently. There's no pressure, no urgency. The universe has a direction. Processes unfold one way, not another, and this directionality is what entropy measures. Entropy is often described as disorder. You may have heard this. A messy room has higher entropy than a tidy one. A shattered glass has higher entropy than an intact one. But disorder is vague, subjective, imprecise. A more accurate way to think about entropy comes from statistical mechanics. Entropy is related to the number of microscopic configurations, the number of ways particles and energy can be arranged, that correspond to the same macroscopic state. A state where energy is spread out among many possible configurations has higher entropy than a state where energy is concentrated in fewer configurations. Think of a gas in a box. If all the gas molecules are squeezed into one corner, there are relatively few ways to arrange them while keeping them all in that corner. But if the gas fills the entire box, there are vastly more ways to arrange the molecules, vastly more microscopic, states that look the same macroscopically. The spread out state has higher entropy, not because it's messier in some aesthetic sense, but because there are statistically more ways for it to exist. Entropy is related to the logarithm of the number of microscopic configurations that realize the same macroscopic state. This connects the laws of thermodynamics, which describe macroscopic systems, to the statistical behavior of microscopic particles. It bridges the large and the small, the visible and the invisible. States where energy is more uniformly spread among many microscopic degrees of freedom have higher entropy than states where energy is highly concentrated. Concentration is rare, diffusion is common, order is fragile, spreading is inevitable. This is why entropy increases, not because the universe prefers disorder in some moral or aesthetic sense, but because there are simply more ways for energy and matter to be spread out than to be concentrated. And in the absence of external constraints, systems naturally explore the configurations available to them. They drift toward the states that are statistically more probable. You don't need to memorize this. You don't need to hold on to the details. Just let the idea settle. Let it rest somewhere in the background of your mind. Entropy measures possibility, measures the ways things can be. And in spontaneous processes, systems tend towards states with more possibilities, more configurations, more ways to exist. Let the word slow. Let your breathing slow. There's no destination, no finish line, just the gentle unfolding of ideas, just the quiet rhythm of explanation. It's worth noting that thermodynamic entropy and information entropy are related but distinct. Information entropy is a concept from communication theory, from the mathematics of data and signals. It shares formal similarities with thermodynamic entropy. Both involve logarithms, both measure uncertainty or possibility. But thermodynamic entropy concerns physical systems, energy distributions, molecular configurations, heat and work and the behavior of matter. Information entropy concerns messages, symbols, probabilities of signals. They're connected, yes, deeply connected in some contexts, but they're not the same thing. For tonight, we're focused on thermodynamic entropy, on the physical world, on energy and its limits, and in that physical world, entropy is not conserved. Unlike energy, which always stays the same in an isolated system, entropy can increase. Does increase in real processes. It measures something different, something about distribution, about accessibility, about the number of ways a system can be. Let yourself drift. Let the distinctions blur if they need to. There's no test, no quiz, no need to remember every detail. Just rest. Just be here. Now we arrive at something profound, something that touches the everyday world in ways you felt but perhaps never named. Irreversibility. The fact that certain processes, once they happen, don't undo themselves, don't reverse, don't return to where they began. A broken egg doesn't reassemble. Spilled milk doesn't flow back into the glass. Smoke from a candle doesn't reconverge into a solid wick. These aren't just practical difficulties. They're not limitations of our technology or our patience. They're expressions of something deeper, something about the way time flows, the way processes unfold. At the microscopic level, the fundamental laws of physics are often time reversal symmetric. If you could watch individual particles colliding, their behavior would look equally valid running forward or backward in time. A collision between two molecules looks the same whether you play the film forward or in reverse. The laws governing their interaction don't prefer one direction over the other, and yet, when we scale up to macroscopic systems with countless billions of particles, irreversibility emerges, not from the fundamental laws themselves, but from the overwhelming statistical likelihood of certain behaviors. It's not that the molecules can't spontaneously reassemble a broken egg. It's that the number of ways they could do so is vanishingly, incomprehensibly small compared to the number of ways they remain broken. The reverse process isn't forbidden, it's just impossibly unlikely. This is where entropy generation comes in. Entropy production, the quantitative measure of irreversibility in real processes. When heat flows from a hot object to a cold one, entropy is generated. When friction slows a moving object, entropy is generated. When gases mix, when chemicals react, when energy spreads and diffuses, entropy is generated. Real processes that happen at finite speeds with real materials in real conditions generate entropy. They make entropy. They increase the total entropy of the universe, and this generation of entropy is what makes them irreversible. Entropy generation is associated with lost opportunities to extract work. Once entropy is produced, that portion of energy can no longer be fully converted back into useful work under the same conditions. The work capacity has been degraded, spent, dissipated into forms that are no longer accessible. Think about friction again. When you slide a book across a table and it comes to rest, the kinetic energy of the book doesn't vanish. It becomes heat. Tiny random motions of molecules in the book and the table surface. The total energy is conserved, but the organized directional motion has become disorganized, random, thermal, and you can't gather up all those random molecular vibrations and turn them back into coherent motion. Not without expending additional energy from somewhere else. Not without creating even more entropy in the process. The entropy generated in that sliding motion represents a permanent change, a step in a direction that doesn't reverse. You can push the book again, yes. You can give it more kinetic energy, but the entropy already created, that remains, that accumulates, that adds to the total. Let yourself rest here. Let the idea settle without force, without effort. Irreversibility isn't a failure of nature. It's not a flaw. It's simply how macroscopic processes work, how time flows, how the universe moves from one moment to the next. There's a concept in thermodynamics called a reversible process. But it's important to understand what this means. A reversible process is an idealization, a mathematical limit, a benchmark that real processes can approach but never quite reach. For a process to be truly reversible, it would need to occur infinitely slowly, with infinitesimal gradients, zero friction, perfect insulation. Ideal conditions that exist only in theory. In a reversible process, no entropy is generated. The system and its surroundings can be returned to their exact initial states without any net change anywhere. Perfect efficiency, perfect control, perfect delicacy. But this requires conditions that can never be fully realized. In practice, every real process happens at some finite rate. Every real material has some friction, some resistance, some imperfection. And so every real process generates entropy. Every real process is to some degree irreversible. Reversible processes serve as benchmarks, as theoretical limits against which we measure real performance. Engineers calculate the reversible work for a process, then compare it to the actual work required, and the difference tells them how much entropy was generated, how much efficiency was lost. But the reversible process itself, it's a guide, a standard, but not a physical reality. You don't need to hold on to every detail. You don't need to remember the distinctions perfectly. Just let the ideas drift through. Let them settle where they will. Real processes generate entropy. Idealized processes don't. And the difference between them measures irreversibility. Breathe. Rest. Let the words continue without grasping at them. Now let's return to that fundamental distinction, the one that underlies everything we've been circling, the distinction between total energy and usable energy, between energy that exists and energy that can do work. Classical thermodynamics combines the first law and the second law through concepts called free energy potentials. These are mathematical constructs, yes, but they represent something tangible, something real. Free energy, whether we're talking about Helmholtz free energy or Gibbs free energy, is, in essence, energy minus the part inevitably tied up with entropy at the ambient temperature. It's the portion of energy that's still available, still accessible, still capable of performing useful work. You can think of it this way. Total energy includes everything. All the kinetic energy of molecules, all the potential energy stored in chemical bonds, all the thermal vibrations, everything. But not all of that energy is available to do work at a given temperature. Some of it is bound up in the randomness, in the entropy, in the countless ways particles can be arranged and moving without producing any net effect. Free energy is what's left after you account for that entropic binding. It's the energy that can still be harnessed, still directed, still used. In spontaneous processes under specified constraints, say constant temperature and pressure, free energy decreases, even as total energy remains constant. The system is losing its capacity to do work, not losing energy, losing useful energy. There's a related concept called exergy. Exergy is the maximum useful work obtainable from a system relative to a chosen environment. Every bit of energy has two parts: exergy, the useful portion, and anergy, the non-usable portion tied to entropy. As processes occur, as entropy is generated, exergy is destroyed, converted into anergy, rendered inaccessible. Exergy analysis is a tool engineers use to understand where in a system the most work capacity is being lost, where entropy generation is highest, where efficiency could potentially be improved. But no matter how much you improve, you can never eliminate entropy generation entirely in a real process. You can reduce it, minimize it, approach the reversible limit more closely, but you can't reach it. Not fully, not in practice. In any real process, exergy is destroyed due to entropy generation. Some of the potential to perform work is irreversibly lost. Lost not in the sense of vanishing, energy doesn't vanish, but lost in the sense of becoming unavailable, becoming bound to entropy, becoming part of the thermal background that can't be easily tapped. Let the words wash over you. Let them settle without effort. There's no urgency, no need to master the concepts. Just let them be present. Let them exist alongside you as you rest. This distinction between energy and free energy, between conserved energy and usable energy, is why we can't simply recycle all energy, why perpetual motion machines don't work, why heat engines are never perfectly efficient. The energy is there, always there, conserved, real, but its ability to do work, that fades, that diminishes, that degrades with every irreversible process. And most processes are irreversible. All real processes are irreversible to some degree, which means that usable energy is constantly being degraded, constantly slipping into forms that are less and less accessible. This isn't a cause for despair, it's not a tragedy, it's simply the way the universe works, the way energy flows, the way time moves forward. And understanding it, understanding this interplay between conservation and degradation, between energy and entropy, that's one of the deepest insights thermodynamics offers. Rest here. Let your mind rest. Let the ideas rest. There's no destination, no goal to reach. Just the quiet unfolding of understanding, the gentle rhythm of explanation. One of the clearest manifestations of the second law is heat flow. Heat flows from hot objects to cold ones, always, spontaneously, naturally, never the reverse. When you place a hot cup of tea in a cool room, energy flows as heat from the higher temperature tea into the lower temperature air. The tea cools, the air warms slightly, and eventually they reach the same temperature, thermal equilibrium. At thermal equilibrium, temperatures have equalized. No net heat flows. The system is at rest, in a sense, stable, unchanging, and crucially, the total entropy of the system has increased during this process. When energy flows as heat from high temperature to low temperature, the entropy gained by the cold object is greater than the entropy lost by the hot object. The total entropy of the combined system increases. This is always true for spontaneous heat flow, always. And once thermal equilibrium is reached, while total energy is conserved, the tea plus the air have the same total energy they started with. The system's capacity to produce additional work by exploiting temperature differences is minimized. The temperature difference is gone. And without a temperature difference, you can't run a heat engine. You can't extract work from thermal energy alone. This is a fundamental limit, a limit that derives from the deep connection between temperature differences, heat flow, and entropy changes. Many engineering limits stem from this. The Carnot efficiency, for example, the maximum theoretical efficiency of a heat engine operating between two temperatures, comes directly from the requirement that entropy not decrease. A Carnot engine is a reversible engine. It generates no entropy. And even this idealized perfect engine can't convert all heat into work. It must reject some heat at a lower temperature. The hotter the high temperature reservoir and the colder the low temperature reservoir, the more efficient the engine can be. But it's never 100%, never perfect, never complete conversion. Real engines are worse than Carnot engines. Real engines generate entropy through friction, through finite rate heat transfer, through all the imperfections of real materials and real processes. But even the best imaginable engine, the reversible Carnot engine, is limited by thermodynamics, by entropy, by the second law. Let yourself sink into this understanding, let it be background, let it be something you don't need to actively think about, just something that rests gently in awareness. Heat flows from hot to cold, energy spreads, temperatures equalize, and in the process the capacity to do work diminishes. This is the dance of energy and entropy, the interplay of conservation and degradation. You don't need to remember the details. You don't need to hold on to specific examples. Just let the pattern settle. Let the rhythm of the universe's unfolding be present. Spontaneous processes move toward equilibrium, toward evenness, toward states where differences have been smoothed out, where gradients have flattened, where energy is more uniformly distributed. And in those states, while energy is still present, its usefulness has diminished. This is why energy, once degraded to low temperature heat near environmental conditions, is so difficult to recover. It's not that the energy is gone, it's that it's now spread out among countless degrees of freedom at a temperature close to the surroundings. There's no gradient to exploit, no difference to harness, no way to extract work without creating even more entropy elsewhere. Rest, breathe, let the ideas float past you like clouds drifting across a calm sky. Let's ground these abstract ideas in everyday examples, in things you've experienced, things you've felt, things that are familiar. Because thermodynamics isn't just an abstract science, it's the science of why your phone battery dies, why your car needs fuel, why food spoils, why ice cubes melt. Consider a heat engine, a car engine, a power plant turbine, any device that converts heat into mechanical work. Fuel is burned, chemical energy is released. This energy has high free energy content. It's organized, concentrated, capable of doing substantial work. But only a fraction of that fuel's chemical energy can be converted into mechanical work. The rest is rejected as waste heat of the environment. This isn't an engineering failure. It's not poor design, it's thermodynamics. In heat engines, only a fraction of the fuel's chemical energy can be converted into mechanical work. The rest is rejected as waste heat of the environment, consistent with the second law. The second law requires this: entropy must increase, heat must be rejected, some energy must be degraded. A typical car engine might convert 25 to 30% of the fuel's energy into useful motion. The rest becomes heat in the exhaust, heat in the cooling system, heat lost to friction. That heat energy is real, it's conserved, but it's no longer useful for propelling the car. It's been dispersed, degraded, tied up with entropy. Or consider a battery. When a battery powers a device, chemical reactions occur inside the battery. Chemical free energy is converted into electrical work, which then powers circuits, lights, motors, screens. but eventually the battery depletes. The chemical reactions have progressed toward equilibrium. The free energy has been used up. The total energy content of the battery hasn't changed dramatically, but the free energy, the portion available to do electrical work, has been consumed, converted into dispersed heat, into entropy. Recharging the battery requires input of additional ordered energy from outside, electrical energy from the grid, and that recharging process generates entropy too, both in the battery and in the power plants that produce the electricity. Nothing has been lost, energy is conserved, but something has been degraded. And that degradation is permanent unless we supply more free energy from elsewhere. Or think about friction. When you rub your hands together, they warm up. Kinetic energy, the organized motion of your hands sliding past each other, converts into thermal energy. Random microscopic motions of molecules in your skin. This is entropy generation in action. Friction in mechanical systems converts organized kinetic energy, coherent motion, directional motion into microscopic random motion. Thermal energy, heat. The entropy increases, the usable energy decreases. You can feel the warmth, you can measure the temperature rise. The energy is there, but you can't gather up that thermal energy and use it to spontaneously move your hands again. The work capacity has been lost, dissipated, converted into a form that's no longer organized, no longer directed, no longer useful for doing mechanical work. These examples, engines, batteries, friction, are everywhere. They're constant. They're the texture of daily life. And in every case, entropy increases and free energy decreases. Always, without exception. Let the examples drift through your mind. Let them connect to your own experiences. Let them be familiar and comforting rather than challenging. There's no need to analyze, no need to dissect, just notice, just recognize. The universe is full of processes like these, processes where energy remains but usefulness fades, where the total is conserved but the accessible portion shrinks. This is the rhythm of thermodynamics, the pulse of entropy, the direction of time. Now let's widen our view. Let's step back from batteries and friction and look at larger systems, more complex systems, systems that seem, at first glance, to defy entropy's relentless increase. Living organisms, ecosystems, planetary atmospheres, weather systems. These systems maintain structure, they maintain organization, they create order out of disorder, pattern out of randomness. A seed grows into a tree. A single cell divides and differentiates into a complex organism. Clouds form, storms organize, climate patterns emerge. Doesn't this contradict entropy? Doesn't this violate the second law? Not at all. And understanding why is one of the most beautiful insights thermodynamics offers. The key is to remember that the second law applies to isolated systems. Systems that don't exchange energy or matter with their surroundings. But living organisms, ecosystems, planets, these are not isolated systems. They're open systems. They take in energy, they export entropy, they maintain themselves far from equilibrium by continuously processing flows of energy and matter. A tree doesn't violate the second law by growing. Yes, the tree becomes more organized, more structured. Its entropy, considered in isolation, decreases as it develops from a simple seed into a complex organism. But the tree doesn't exist in isolation. The tree absorbs sunlight, high-quality, low-entropy energy from the sun. The tree uses this energy to build structure, to synthesize complex molecules to maintain itself, and in the process the tree releases heat, low quality, high entropy energy back into the environment. The tree's entropy may decrease, but the entropy of the tree plus its surroundings, the sun, the air, the soil, the radiated heat, increases. The total entropy increases as the second law requires. The tree maintains order by exporting disorder, by exporting entropy. This is how all living systems work, all ecosystems, all organized structures far from equilibrium. They're not closed loops, they're not perpetual motion machines, they're throughput systems. They take in free energy, they use it to build and maintain structure, and they export entropy-laden waste. Thermodynamic analyses show that biological and ecological systems operate far from equilibrium by continuously dissipating free energy, for example, from sunlight or chemical gradients, and generating entropy in their surroundings. They maintain themselves in improbable, organized states by creating even more disorder elsewhere. The entire biosphere of Earth operates this way. Sunlight streams in, low entropy, high quality energy. Life captures some of this energy through photosynthesis, uses it for growth and metabolism and reproduction, and in the process heat is radiated back into space. High entropy, degraded energy. Infrared radiation carrying away the waste entropy. The Earth itself is not in equilibrium. It receives energy from the sun at high temperature and radiates energy back into the cold of space at much lower temperature. This flow, this gradient, is what allows life to persist. If the Earth were in thermal equilibrium with its surroundings, no life would be possible. No organization, no structure, just uniform, featureless thermal bath. But the Earth isn't in equilibrium. The sun provides a constant source of free energy, and life exploits this gradient, this flow, to build and maintain complexity. Let yourself rest with this. Let the idea settle. There's no contradiction, no violation, just a more complete picture. Entropy increases in the universe as a whole, always, but locally, temporarily, in open systems fed by external energy sources, entropy can decrease. Organization can emerge. As long as more entropy is exported than is reduced internally, as long as the total still increases. Planetary atmospheres and climates follow similar principles. The atmosphere is not in equilibrium. It's constantly driven by energy from the sun, by temperature differences between equator and poles, between day and night, between land and sea. These temperature differences, these gradients, drive atmospheric circulations, winds, currents, weather systems, storms, and these circulations transport heat. They redistribute energy. They flatten gradients. Planetary atmospheres and climate can be studied in terms of competing roles of energy input, radiative loss, and entropy production. Atmospheric circulations transport heat and increase entropy in the process. The wind doesn't blow to increase entropy, but entropy increases as a consequence of the wind blowing, as a consequence of heat flowing from warm regions to cool regions, as a consequence of organized motion degrading into turbulence and eventually heat. Weather is a manifestation of entropy production, of the atmosphere's attempt, in a sense, to reduce temperature gradients, to spread energy more uniformly. A storm forms when warm, moist air rises and cold, dry air sinks. Energy is redistributed, latent heat is released, winds blow, rain falls, and entropy increases, always increases. Eventually, if the sun were to stop shining, the atmosphere would settle into equilibrium, temperatures would equalize, winds would cease, weather would stop. But as long as the sun shines, as long as energy flows, the atmosphere remains out of equilibrium, and entropy is continuously produced as that energy flows and degrades. Even highly organized systems, living organisms, technological infrastructures, cities, civilizations, ultimately obey the second law. Maintaining order requires a continuous throughput of free energy, and that throughput leads to net entropy increase in the environment. A city doesn't violate thermodynamics, but it only remains organized, only continues functioning, because energy flows into it constantly. Electricity from power plants, fuel for vehicles, food for inhabitants, materials for construction and maintenance, and entropy flows out. Heat, waste, exhaust, degraded energy radiating away. Cut off the energy supply and the city would decay. Structures would crumble, order would fade, entropy would increase unchecked until everything reached equilibrium with the surroundings. Maintenance requires energy. Organization requires energy. Fighting entropy requires energy. And using that energy always generates more entropy elsewhere. Let the scope of this settle. Let the universality of it rest gently in your awareness. From the smallest living cell to the largest ecosystem, from weather systems to entire planets, from organisms to civilizations, all of them operate far from equilibrium. All of them maintain order by exporting entropy. All of them obey the second law when you account for their surroundings. There's something almost poetic about this, something beautiful in the realization that life, organization, structure, all the things we value, all the complexity we see around us emerge not by defying entropy but by channeling it. By riding the flow of energy from high-quality sources to low-quality sinks, we exist in the gradient, in the flow, in the temporary eddies of organization that form when energy passes through. And as long as energy flows, as long as the sun shines, as long as gradients exist, structure can persist, but only by continuously consuming free energy. Only by continuously exporting entropy. There's no perpetual organization, no permanent structure without ongoing energy input. Everything must be maintained. Everything must be fed. Everything must export its disorder. Rest here. Let the cosmic scale settle. Let the deep interconnection of all organized systems wash over you gently. There's no need to hold on to every detail, just let the pattern be present. Let the understanding rest in the background. Now we come to an important question, one you might be wondering. If entropy always increases, if processes are irreversible, if free energy always degrades, can anything be reversed? Can any energy be recovered? The answer is subtle, nuanced. Not a simple yes or no. Some processes can be partially reversed, but only by consuming additional free energy, only by generating more entropy elsewhere. Consider a refrigerator. A refrigerator moves heat from a cold interior to a warmer exterior. It makes the cold space colder and the warm space warmer. This appears to violate the natural direction of heat flow. Heat naturally flows from hot to cold. But here we're moving it from cold to hot. This is allowed. It's possible. But it's not spontaneous. It requires work, electrical work to run the compressor, energy input to drive the process. Devices such as refrigerators and heat pumps move heat from colder to hotter bodies, apparently reversing natural heat flow. but they do so only by consuming external work and causing greater entropy increase in the combined system. The entropy of the refrigerator's interior decreases as it cools, but the entropy generated by the work input, the electricity production, the heat rejected to the room, the inefficiencies in the motor, more than compensates. The total entropy still increases. You can reverse local processes, you can create local order, you can move energy uphill from low quality to high quality. But you can't do it for free. You can't do it without creating more disorder somewhere else. This is the pattern. This is the rule. Local decreases in entropy are possible, but only at the cost of larger increases elsewhere. You can unmix a solution by distillation. You can separate cream from milk. You can compress a gas back into a smaller volume. But every one of these processes requires energy input, requires work, and generates entropy in the process. The net result is always positive. The total entropy always increases, even when we clever humans design systems to locally reverse what seems natural. We're not defeating entropy, we're just moving it around, concentrating it here by dispersing it more elsewhere. At a more fundamental level, there's something called fluctuation theorems. These are results from non-equilibrium statistical mechanics that describe how entropy behaves in small systems over short timescales. Fluctuation theorems and non-equilibrium thermodynamics show that while small temporary decreases in entropy can occur in microscopic systems, the average behavior over time still respects the second law. In a tiny system, a single molecule, a microscopic particle, you might observe brief moments where entropy appears to decrease. A molecule might spontaneously move against a concentration gradient. A particle might momentarily gain energy from its surroundings without doing work. These are fluctuations, statistical variations, random events that are allowed by the probabilistic nature of microscopic systems, but they're rare, brief, and they average out over time. For macroscopic systems, systems with billions or trillions of particles, these fluctuations become vanishingly unlikely. The probability of spontaneously reversing a high entropy state into a low entropy one is so tiny that it's effectively zero. For macroscopic systems relevant to everyday life, the probability of spontaneously reversing a high entropy state into a low entropy one is so tiny that it is effectively zero over cosmic timescales. You won't see spilled milk spontaneously gather itself back into a glass, not in a billion years, not in the lifetime of the universe. It's not impossible in principle. The molecules could, by pure chance, happen to move in just the right coordinated way. But the probability is incomprehensibly small, so small that it might as well be impossible. This is the power of large numbers, the overwhelming, statistical weight of high entropy states. When you have trillions of particles, the number of ways they can be arranged in a disordered state is astronomically larger than the number of ways they can be arranged in an ordered state. And so disorder wins, entropy increases. Spontaneous ordering is so unlikely that we never observe it in practice. Let yourself rest with this understanding. Let the statistical nature of entropy settle gently. It's not that the universe forbids broken eggs from reassembling. It's that the universe makes it so statistically improbable that it never happens. The laws don't prevent it. The numbers do. Breathe. Rest. Let the ideas drift. so complete recovery of initial free energy content is impossible for real macroscopic processes. Once you've burned fuel in an engine, once you've discharged a battery, once you've let heat disperse into the environment, you can't fully recover what was lost. Not without putting in at least as much free energy as you lost. Usually more. You can recharge a battery, but it takes more energy to recharge than the battery will deliver when you use it again. Some energy is lost to heat in the charging process. Some free energy is degraded in the resistance of the wires, the chemical reactions, the inefficiencies. You can recycle heat using a heat pump, but the work required to run the pump generates more entropy than you reduce by collecting the heat. Energy is conserved, always. But free energy is not. Usefulness is not. Work capacity is not. That's the fundamental asymmetry. That's why perpetual motion machines don't work. That's why we need continuous energy inputs to maintain our technological civilization. Every process degrades some free energy. Every real transformation generates some entropy. And while we can be clever, while we can be efficient, while we can minimize losses, we can never eliminate them entirely. Thermodynamics sets limits, absolute limits, limits we can approach but never breach. Rest here. Let the finality of these limits be gentle rather than harsh. There's no tragedy in limitation, just reality, just the way things are. The universe has rules, patterns, boundaries, and understanding them is not confinement but clarity. The second law is firm, established, well supported by centuries of observation and experiment. But it's also worth acknowledging that thermodynamics continues to develop, to refine, to extend into new domains. While the second law itself is well established, there are ongoing refinements in non-equilibrium thermodynamics, in how we understand entropy production in systems driven far from equilibrium, in how entropy connects to information in quantum systems and nanoscale devices. Contemporary research in non-equilibrium thermodynamics and quantum thermodynamics refines how entropy production and free energy changes are quantified in driven and microscopic systems. But these refinements remain consistent with the second law's basic directionality: new mathematics, new formalisms, new ways of calculating and predicting. But the core truth remains: entropy increases in spontaneous processes. Free energy degrades. Irreversibility is real. The relationship between thermodynamic entropy and information theoretic measures continues to be clarified, especially in contexts like computation, where information processing has thermodynamic costs. Erasing information generates entropy. Copying information requires energy. These connections are deep, fascinating, still being explored, but they don't imply that entropy can be freely recycled without cost. They don't overturn the basic principles. They extend them, refine them, apply them in new contexts. The second law stands. Across standard physics frameworks and educational sources, the mainstream view remains that energy conservation and entropy increase together explain why some energy can never be fully recovered for work once it has degraded to near equilibrium forms. This is consensus. This is established. This is the understanding that emerges from theory, experiment, and application. There's always more to learn, always deeper questions to ask, always new systems to study, but the fundamental pattern is clear, has been clear for over a century, will remain clear as science advances. Energy is conserved, entropy increases, Free energy degrades. Processes are irreversible. Work capacity is lost. These aren't opinions, aren't theories that might be overturned tomorrow. They're as close to certain as anything in science can be. Let this certainty be comforting. Let the solidity of the laws be grounding rather than restricting. The universe has structure, patterns, regularities, and we've been privileged to uncover some of them, to understand some of them, to name them and describe them and use them to build our world. Thermodynamics is one of the great intellectual achievements of humanity, a framework that spans from steam engines to black holes, from living cells to the cosmos, from the dawn of the Industrial Revolution to the frontiers of quantum mechanics. And at its heart are these simple, profound truths about energy and entropy, about conservation and degradation, about what can and cannot be done. Rest now. Let the ideas settle into place. Let them form a quiet background understanding. You don't need to remember every detail, every example, every nuance. Just let the core pattern rest gently in your awareness. Energy persists, but usefulness fades. The total remains, but the accessible portion shrinks. This is why batteries die. Why engines need fuel. Why we can't recycle all energy. Why there's an arrow of time, not because energy vanishes, but because it degrades, spreads, equalizes, becomes bound to entropy, becomes part of the low-grade thermal background that can no longer drive change. The universe tends toward equilibrium, towards sameness, towards states where nothing more can happen because all differences have been erased, all gradients flattened, all free energy spent. But we're not there yet, not even close. The sun still shines, stars still burn, energy still flows, and in that flow, in those gradients, life persists. Structure emerges, complexity unfolds, temporarily, locally, always exporting entropy, always riding the current of degrading energy, but raiding it nonetheless, making use of it, building beauty and meaning and understanding in the brief time before equilibrium. Let yourself rest now, fully, completely. Let the science dissolve into background. Let the details fade. Just rest in the quiet knowledge that the universe has patterns, that those patterns can be understood, that you've spent this time moving through one of the deepest patterns of all, the pattern of energy and entropy, of conservation and irreversibility, of why some things happen and others don't, of why time flows forward and never back. There's nothing more you need to learn tonight, nothing more you need to remember, nothing more you need to grasp or hold or understand. Just rest, just breathe, just be. The universe will continue its slow drift toward equilibrium. Entropy will keep increasing. Free energy will keep degrading. But not tonight. Tonight these are just ideas, just words, just gentle thoughts drifting through a quiet mind. Let them drift. Let yourself drift into rest, into sleep, into the quiet darkness where understanding dissolves into peace. Energy is conserved, entropy increases, and you can simply rest.